Okay, welcome to day 2, and we're going to do calculations of specific heat. And those of you that had Mr. Mayberry or me last year, this is just review, so we won't spend a whole lot of time. If you have any questions, make sure you ask in class. Here's the formula. So the heat is equal to the specific heat times the mass times the change in temperature. Well, here we go through all of them. In kilograms, so mass is in kilograms. Temperature is going to be the change in temperature, and so we always want that to be a positive, we hope. And then the specific heat of the substance. And all we're going to do is follow it and plug in what we know and solve for what we don't know. And it's pretty straightforward. That's going to let us talk about what's going on as compounds and elements go through phase changes. And so when we have a solid and we add enough energy, we can actually break intramolecular bonds, so the bonds between molecules or between atoms, and cause them, instead of being a rigid formation, to be in a fluid formation, which would be our liquid. Or we can even add more energy and cause the change in the relationship of the liquid, so these molecules sliding past and having passing interacting forces involved into being completely separate and going into a gaseous phase. So we need energy to do that, and so here is a real good demonstration in this slide that shows you all of that, and you probably could think of a lot of different ones. If you remember when we've done this before, when you go through a phase change, you have a plateau on your graph. And our graphs are always have the same look. We'll try over here. Okay. I'll have a slanted part. So that is when we have a change and we're just adding heat. And then when we have a phase change, we get a plateau. And it's melting. It heats up once it's all melted. And the liquid gets warmer and warmer until we get another plateau, another phase change, and then we go into the gaseous phase. So each of these plateaus is involved in the actual phase change, and we're going to look at the latent heat. Energy is required to change that because we know that if we melt ice, it continues to take energy in until it is all melted. And if you watch a thermometer, you can watch it plateau very easily and until it all becomes changed. And that's actually one of the ways that you can tell the identity of a substance. If you just caused to go through a phase change, look on a chart and you would be able to link the temperature at which those phase changes occur with the substance. And so that's one way you can identify them. So if we go from a solid to liquid or a liquid to a solid, we call it the latent heat of fusion. And then if we cause it to go from a liquid to a gas or back, then we call it heat of vaporization. And so we will use those values when we are doing the calculation. So you've got to think about where are you on this phase change diagram. So there's the formula this time. We're going to use heat again, and it's the mass times the heat of fusion or the heat of vaporization, again, depending on where you are on that phase change diagram. And we've got joules, mass is still in kilograms, and then we're going to get this information from a table. And that table will always be provided to you. You're not expected to remember these, but you'll do a lot of practice, and some of these you do start to remember with use. Here is that phase change diagram done very, very nicely. And you can see that we have a solid, very rigid structure, and very, very definite. And as we raise the temperature, and you can think about it, you can put a block of wood into the freezer and take energy away from it, make it colder, and it's not really going to do anything except lose energy and still be a solid. Once you get it to a temperature, and we think about ice this way, I can continue to pump energy into it, and it will change and start to melt, but it will plateau as far as the temperature. And so then I know a phase change is occurring. Then as I get it past that phase change, so once it's all liquid, then you'll see that rise in temperature again until you reach the point where it has enough energy to break the intramolecular bonds so that it can go into a gas, another plateau, and then it becomes a gas. And then you can follow it as well, going the reverse direction. So you really do, we always encourage you on all of your problems is to go ahead and draw yourself a real quick phase change diagram and put your temperatures. So if I know water's the one that I always know the temperatures for, so if I start at solid ice at minus 10 degrees and I want to know how much energy it takes until it gets to, this would be degrees Celsius, until it gets to 113 degrees, I know I need to figure out the temperature between 0 and minus 10. I have two latent phases, so I've got a heat of fusion and I have a heat of vaporization, where the only thing that matters is those variables and the masses. And then I also need to do a temperature change between 100 degrees and 0 degrees. So there is my heating up of my liquid. And then once it's all turned to steam, I still have to worry about one more temperature change, which is going to be that between 113 and 100 degrees. So we'll go through practices like that. But doing a little diagram and so you know exactly what you need to do will really help you go through that problem very, very clearly. Okay, we're going to stop here because I don't want the video to be too long. And this is one of the topics, and this is what we'll be practicing on in class. So good luck.